what are the meanings and formulas for the following business concepts? So let's talk typical, right? So like what would typically be your cost formula? I'll say the cost of Q quantity. What typically kind of cost function would have? That's revenue. Price times quantity is revenue, yeah. But I mean, price times quantity, it also applies to cost. That is the variable cost. So you have the variable cost, right? That is price times quantity. That's the price per item, and that's the quantity of items. So I mean, that's also, is that what you meant? Oh, okay, well that's fine. Okay, say that again for revenue. So you have the fixed cost, and then you have the flat cost, right? So that's one type of cost function that we often see is just a linear cost function, where you have a sunk cost or a fixed cost and then a variable cost. But we have lately been seeing other types of cost functions like quadratic cost functions, which are typically just some quadratic facing up, right? Because the cost function dips and then it goes back up again. So those are two different cost functions we've been seeing. How do we create the average cost function?
Is it the same thing but divided by the?
Right, it's just the cost function itself divided by Q. That makes a lot of sense because if you were looking, for example, at the cost of 10 items, then you would divide by 10 items and that would give you the average cost for each item. Okay, what about marginal cost? What does that word marginal mean again? It's the very next item. And so there's two ways to calculate marginal cost. Let's say that you want the marginal cost of the X item, then you would just subtract out the cost of the X minus 1 items that came before it. Or you could just take the derivative of the cost and plug in that item that you're looking for. So that's your marginal cost. Okay, then revenue.
Prices.
Yeah, that's price times quantity. So your revenue for each quantity is your price times quantity. And the price function can often be written in a way other than just P. That could be D of Q. So D of Q is your demand function, which tells you the price you should charge. And then there's your quantity. All right, and then finally our profit formula.
Revenue minus cost.
Yeah, revenue minus cost. We have our profit, profit of a certain quantity would be revenue minus cost. Now you can see that I've been using Q or X. I kind of switch back and forth without thinking about it. Like here I did Q, and then I went right to X, and then here I was doing X, but then here I was doing Q. They're both used. You can see a Q or an X. Okay, so there's our standard formulas, and remember marginal applies to anything, not just cost. So that could have been the marginal revenue, where I just used R instead of C, or it could have been R prime X, or that could apply to profit as well. So then that would be P minus X minus 1 and P minus. Okay, and then finally, how do you find all the following things? So how do you find the Y coordinate for anything? You just stick it into the original function, that'll tell you the Y coordinate. And how do you find maxes and mins? Set what to 0? What equal to 0?
X equals.
Well, X equals 0 is just a particular X value. There's X equals 0. But if we want to find maxes and mins, that means we're looking for what kind of spots on the graph? We're looking for flat spots, and we do that by looking at the which function?
X.
We have three functions, f of x, f prime of x, and f double prime of x. Which one will tell us about a flat spot? Yes, exactly. So f prime of x will tell us about flat spots, and that would be maxes or mins, because f prime is talking about slope. And so that's what that will tell us. And then how do we find inflection points? The what? Yeah, the second derivative is going to tell us about concavity, and so that's going to tell us about inflection points. So we'll set that one. Okay, and then finally, if we set f of x equal to 0, what is that finding? Not critical points are where anytime f prime of x is equal to 0 or undefined. Thank you for saying that. So these are critical points. X-intercepts, that's right. When f of x equals 0, that's going to be your x-intercepts. Okay, boy, this is a lot of really dense information right here, isn't it? Like that's definitely well worth tattooing on your face or somewhere. So that you always remember what each function is offering. So f of x is offering the y coordinates. F prime of x is offering the slope. F double prime of x is offering the concavity. which means in every case you set that function equal to 0 or undefined, and that'll help you find x-intercepts, flat spots, or inflection points. Yep. Okay, a lot of information that we're dealing with. These are all new concepts. Alrighty, so where are we today? Today is March 5th, and we're going to wrap up chapter 2 today. So we'll finish 2.9, finish 2.10, and then I gave you the practice test over there, so we can probably look at a few problems from there. And then otherwise, you take your test on Thursday, so 2 more days to study for that test. And then you'll all go home and have a marvelous spring break. And of course, since we're all adults, that means you'll work, but at least you have a couple days off school. Wasn't that nice when you were in high school or before and you had spring break and you just did nothing? Now that I'm a parent, I wonder, what did those parents do with those kids all week long? I mean, when kids, like nowadays, we have a daughter who's in school, and when the school goes on vacation, I'm like, oh, what are we gonna do with this kid for a week, right? So it's very different how considerations change over time. All right, I'm kidding, but the way I said that, that's supposed to be a joke. All right, so I already told the nose joke, so why does Waldo wear stripes? Why does Waldo wear stripes? Do you all know who Waldo is?
Yeah.
Yeah.
Just in case you don't.
No, because nobody can find them.
Yeah, you can't find it. So let's see. And by the way, I thought it was Waldo. Where's Waldo? But lately, it's now where's Wally?
The book says Waldo.
Yeah, the book says Waldo. Very confusing. So the whole idea is that you would look in that and try to find Waldo. Did you all do that as kids?
Yes.
Yeah.
Maybe you did, maybe you didn't. So Waldo, the tricky thing is that he's really hard to see. Like, that's what he looks like. And so you see he wears stripes. And it's, oh, here's an example. Like, this is a very small scene. Can you find him? Well, yeah, I don't see him yet. Did anyone see him? It'd be funny if he's not even in this picture. Because this is just zoomed in on one particular small spot. Yeah, I don't see him at all. Anyway, so why does Waldo wear stripes? He doesn't want to be spotted. All right. All right, folks. Well, I think we left off on number 11, didn't we? We got as far as, I think I told us to skip 10, or did we do 10?
Yeah.
So, well, I think we're at 11.
No, we did.
Oh, we did 11. Oh, wonderful. Okay, so let's do, okay, skip 12. It's a perfectly fine question, but the next one we'll do something similar. So here we go. Number 13, the sunglass hut. First of all, do you all remember the store called the Sunglass Hut?
Yeah.
They used to be in the mall?
They still have it.
Oh, did they really? It's still in business? Oh my gosh, I can't believe it. So the Sunglass Hut company has a profit function given by that, and immediately whenever you see a function, you think about what it looks like. This is an upside down problem. And that makes sense. Because typically the more you make, the more profit you make, but then there's a point of turnaround where you start making less and less profit. And why do you make less and less profit over time? Because unbeknownst to you, well, not to you, your cost function is going up. So as time goes on, your costs are going up, which means your profits will have to come down. Okay, so there's your profit function. Q is the number of thousands of pairs. Let's remember that Q is in thousands. And P of Q is the total profit, also in thousands. So let's remember that both of those numbers are in thousands. And you're selling Q pairs of sunglasses. Now, by the way, a pair of sunglasses. Is that one sunglasses or two sunglasses? Yeah, it's just one thing you put on your face, right? But we call it a pair. And why do we call it a pair? Because there's two eye things, right? It's very misleading. I want to walk in there and demand, where's my pair? I bought a pair. Give me another one for free. Okay, so find a simplified expression for the marginal profit. So marginal profit, keep in mind there's two ways of doing it. The one way you could do it is the marginal profit for Q items. That would be P of Q minus P of Q minus 1. And that would be the technical definition of marginal profit. However, that's a little unwieldy. Like if we actually plugged q minus 1 into that whole thing, can you imagine? This would be really unfortunate. You'd have negative 0.02 q squared plus 6q minus 49. And then minus, and then you plug q minus 1 into all that. So negative 0.02 q minus 1 squared plus 6 q minus 1 minus 49. Okay, so can you see? That's what it would actually look like. And then you'd have to FOIL that and then distribute. And so you can see that there'd be a lot of messy detail work, which is why instead of doing that, they just do p prime of q. It's a whole lot simpler than actually doing all of that. I mean, part of me is tempted to finish that, but there's no need to do all that extra work. That's why we have the derivative to tell you a number that's approximately close to what you would have gotten if you had done that. So the marginal profit is simple. It's just negative 0.04 q plus 6. So I hope you all can appreciate how much easier and faster that was than actually simplifying this. Hey there, Rosa. Okay, well, that's marginal profit. How many pairs of sunglasses should be sold to maximize profits? So if we want to maximize profits, what point are we looking for? Yeah, we're looking for this critical point right up here at the top, which means we want to find when the derivative is equal to 0. So when is the derivative equal to 0? We already found an expression for the derivative, so it's asking when is negative 0.04q plus 6 equal to 0. And so I'm going to move the 6 over, negative 0.04q equals negative 6, and then we divide both sides by negative 0.04. And we get q equals whatever that is. Which is 6 divided by 0.04. So that's 150. Oh, much better. Now what does that mean actually? How many sunglasses is that? Is that 150 sunglasses? Is it 150 pairs of sunglasses? What did it say about our units? Q is thousands. So that's actually 150 thousands of sunglasses. You can avoid the whole issue by just calling them sunglasses. I don't know what don't call pairs of sunglasses. Okay. And then it says, what is the actual maximum profit? So that's just telling us Q. Q is 150,000 sunglasses. So now how do I actually find the profit? Yeah, we just plug it in. Now what do I plug in? Do I plug in 150 or do I plug in 150,000? Just 150. See, they did all this just to make the numbers easier. All right, so we plug in 150 and then that'd be negative 0.02 times 150 squared plus 6 times 150 minus 49. And that will be the actual amount of profit that you get when you are maximizing profit. So let's see here, that's negative 0.02 times 150 squared plus 6 times 150 minus 49. And that came out to be 401. It seems like not a lot, but 401 is really $401,000. Now that seems like a little more. Now, however, is that really a lot of profit? How many sunglasses did we sell? 150,000. So let's wonder, what is the average profit? So what would be your average profit? You would just take your actual profit, 401,000, and divide by your actual number of sunglasses. This is going to be painful. All those zeros cancel out, and we have 401 divided by 150. How much profit did you make per pair of sunglasses? Jeez, $2.67. You what? Yeah, I mean, probably these numbers are just made up, right? These numbers are just made up. It doesn't have anything to do with the actual sunglasses. Because I'm sure that sunglasses are making a lot more profit than that. The sunglasses are just cheap piece of plastic that somebody can make for $2. And then they sell them for hundreds of dollars. Yeah.
Like the profit formula, like implies like everyone's been paid.
Yes.
Okay.
Yeah, and that's the wonderful thing about profit. That's a good point. Profit is after all your employees are paid, your manager's salary is paid, the rent is paid, air conditioning is paid, Investment in the future is paid. Everything is paid. That's just pure profit. Yeah. All right. Well, there we have it. You'll have a problem like that on your test. Then we have what? 14. Okay. One more question. One more business question. So suppose the company's revenue function is given by that, and the cost function is given by that, where Q is in hundreds of units, and R and C are total dollars. So that's nice to know. Q is in hundreds, but the actual revenue and cost are actual dollars. So not in hundreds of dollars or thousands of dollars, but just regular dollars. All right. So find a simplified expression for the marginal profit. So we'll do that. And then how many items need to be sold to maximize profit? And while we're at it, let's actually find the real profit. So what do we need to do? Yeah, so notice they want us to find marginal profit. But what do we need to find before we can find marginal profit? Regular profit. So we need to first set about finding actual profits. P of Q is revenue minus cost. And then we need to actually simplify all that. So that would be P of Q equals revenue negative Q cubed plus 210 Q squared minus, and then make sure you use parentheses, 280 plus 18Q. Why did I use parentheses? To subtract cost?
Because it's a separate expression.
It is a separate expression. I didn't put parentheses on this one, though. I mean, I suppose I could have put parentheses on the first one, but why did I put parentheses on the second one but not the first one?
So you can distribute them.
Yeah, I have to distribute the minus. That would be a very common mistake. So we're going to distribute our minus, so now we have negative Q cubed plus 210 Q squared minus, I'm going to put them in order, minus 18Q minus 2. So that's my profit function. And then we'll take the derivative. Isn't it wonderful that when you take the derivative, the formula gets easier? That's really wonderful. So now here's my P prime of Q, which is what they're calling MP of Q, where MP is marginal profit, which is really defined as P prime of Q. So then we have negative 3Q squared plus 420Q minus 18. So that's just our simplified expression for marginal profit. So now, how many items need to be sold to maximize profits? And what is the maximum profit? So what do? Again, you might want to consider, here's our, well, actually, our profit function was cubic, wasn't it? So it probably did something like that. I actually know it was a negative cubic. So what would that look like? A negative cubic would actually look like that. So that kind of makes sense. That at first, if you sell nothing, you're at negative profit, but then you start selling things and you finally break even. And then you sell more things and you maximize your profit. And then if you keep on selling, you eventually break even again. And if you keep on selling, you just go into debt. So that looks like what the cubic function should look like. So we're looking for this point right here, which is a flat spot. So what do? We just set P prime of Q equal to 0. So keep in mind you have lots of options available to you when you solve a quadratic. You can just do the quadratic formula. You can try to factor. Anyone feel lucky? Think we can factor this thing? What should we divide out? Just the 3?
No.
Yeah, let's divide out the negative 3. So now we have Q squared minus, is that 140Q? And then plus 6. Is that factorable? What multiplies to make 6 that adds to make 140? Probably nothing. So, probably nothing. So, let's do the quadratic formula then. So, we'll have negative b minus square root of b squared minus 4a AC over 2 A. So 140 plus or minus something over 2. Under the square root, did anyone else get 19,576? Which is 140 plus or minus 139.91426 all of 2. And so then that gives us two different answers, two possibilities. One with the minus and one with the plus. So I think I've already told you this, but on your calculator, if you type in parenthesis 140 plus 139.91426, parenthesis divide by 2, then once you have that answer, you can just hit second enter, and it'll pull it right back up again, and then you just change the plus to a minus. And then you don't have to type the whole thing in plus. So I got 39.957 or 4 cents. No, 0.04. Not 4 cents. 0.04. So what do those two numbers represent? What did we just solve for? Are those dollars or those quantities? They're quantities, because what did we just solve for? We just used the quadratic formula to solve for Q, right? We had a Q squared formula, so we just solved for Q. So those are definitely quantities. And what happens at those quantities? Those quantities are when what? When the derivative is equal to 0. So those quantities are where we have a flat spot. So again, if you look at your graph, what that really means is that there was a flat spot right there, just to the right of 0. That was the 0.04 flat spot. And then there was another flat spot way over there at 139. So does everyone see our two flat spots? One flat spot was just barely to the right at 0.04. And the other flat spot was way over at 139. So which one of those flat spots refers to us? Which one of those flat spots is telling us where we maximize profit? Definitely this one, right? I mean, this is a flat spot, but that's not a maximum of profit. That's a minimum of profit. That is a local minimum, because if you keep selling more and more forever, you'll eventually have even worse profit over you. Okay, so now that we know that the answer we want is Q equals 139.957, what do we do with that number? Because that's just how many you have to sell to maximize your profits. Yeah, plug it back into the actual profit formula so that we know how much profit that is. So then you have to go all the way back to your cubic formula.
Repeat the math percent.
That was just part of my decimal expansion, 95713. Did I write those down wrong?
I was just looking at it.
Oh, okay. All right, so then now I'm going to do negative 139. Cubed, I'm plugging it back into my original, plus 210. Third, minus 18. And minus 2. I don't know about anyone else, but I got an answer of 1,369,239 cents. So that's the actual maximum profits. Did anyone else get that number? What's that? Right. So, okay, so good point. So how many items need to be sold? So that's what Q is. So how many actual items is that? So that would be 13,995.7 items. Now we can't sell 0.7 of an item. So what would we need to do? This is very subtle. We would actually have to round that to either 13,995 or 13,996, right? So therefore, what decimal should I have plugged in? either 139.95, just that, or 139.96, just that. All right, so I rounded appropriately according to what the whole number of items could actually be. Does anyone see what I'm saying there? So since I can't have 0.7 of an item, it's either 5 or 6, and then I would plug both of those numbers in and see which one actually did produce the maximum profit. So let me change my calculation here. I'm going to do 139.95. In which case that profit is 136.789.048. Or if I do 0.96, it'd be 1,369.76.68. Now, notice that actually is a big deal, right? Because the computations were in this number, but that represents hundreds. And then by bumping that out and either making that a 5 or a 6, depending on whether you round down or round up, plugging both of those numbers in, what was the difference between your profit? A lot. I mean, how much? Maybe not a super ton, but let's see. 1, 3, 6, 8, 7, 8, 9, 105. That was a difference of $587. And you know what? If that's my fee for telling the company the correct thing that they should do, I'll take the $587. And if that's just free money, I'll take it. And so then what are we saying then? We actually want to make this one, which is 13,996 items. So that would be your recommendation, right? You're the business analyst. They're coming to you to make all these financial decisions. How many should we make to maximize profit? And you'd go to them and say, make exactly 13,996 items. And give me the $587 as my bonus. Because I rounded up instead of rounding down. Okay. Well, folks, we're all done with section 2.9. So now we'll take a look at 2.10. There's a really neat idea in section 2.10, which allows us to make decisions like this a little more succinctly, I believe, when when we're asking how many should I make to maximize profits. There's a nice formula that helps us do that. Any questions before we move on from here? All right, well, let's do it. So section 210, first of all, we're going to skip the first couple problems about tangent line approximation. We're just not going to do those at all, which is totally fine. So everyone skip, and let's get all the way out to here. And before we do number 3, what I'd like you to do is take out a sheet of line paper, and you're going to take some notes with you about what this concept is talking about. The concept we're going to talk about is elasticity. Demand elasticity. We've talked a lot about demand and supply. And so now what we want to do is talk about demand elasticity. And that's actually what this section is called. Elasticity of demand. Elasticity. First of all, is a nice word to say. Elasticity. Okay, so everyone has a sheet of line paper? So what we're going to do is make a little number line and talk about the various values of elasticity. You don't necessarily have to start writing all of them. I'm going to present a little situation over here, and I'd like to write down what I write down. So first of all, let's review some definitions. Q is always referring to quantity, and P is always referring to price. And previously, we had something called the demand function, which was D of Q equals P. This was our demand function. And I want you to notice the order of input-output on this demand function. The input was quantity, so you tell me how many you want to sell, and the output was price. So that was just a particular way of thinking about the demand function. If you tell me how many you want to sell, then this demand function will magically tell you the price you should charge. It will attract exactly that many people to your store to buy exactly that many quantity. So So what I'd just like you to imagine is that you could equally well rewrite this demand function backwards, find the inverse function. And then that would be demand function in terms of P equaling quantity. Meaning, you tell me how much you want to charge. Like maybe you're just set in your ways. You're like, I want to charge $22 for these pizzas. They're that good. So you go ahead and tell me the price I'm going to charge, and then I'll tell you this is how many people are going to show up. Okay? So is that fair that you can write your demand function either way? It really just depends on how you're thinking about your business. If you say, hey, I want to sell 1,000 cars this week, or this month, that's how much I should charge. So you're kind of thinking in terms of your goal of how many you want to sell. Or if you say, hey, this is how much I want to charge because my product is fancy, and this is how much I want to charge because there's prestige involved, then they'll tell you how many people will show up to buy it. Okay, now this is the demand function we're going to use today. So this is backwards from the demand function we used before. If you recall before, we were saying revenue is price times quantity, and we were using D of Q times Q, because D of Q was our price. Whereas now we're looking at D of P equals Q. So we just want to be mindful of the fact that sometimes we see a D of Q equals P, and sometimes we see D of P equals Q, right? All right, so what is elasticity? Given a demand function that gives Q in terms of P, we're going to define this function called the elasticity of demand. So elasticity. We're going to define the elasticity of demand as the equation E equals the absolute value of price divided by quantity times, now you see this part where it says dq over dp? The d means derivative. So it's really just the derivative. Oh my, did I have that written backwards? Probably feels D of Q. P is the input variable. Oh, okay, no, good. Yeah, that's right. So it's times D of P. I'm going to write it like that. I like writing it like that. But. So there's our elasticity formula. It's a new formula we'll use just in this last section, section 2.10. So when you actually use this formula, using your demand function and the price that you chose and the quantity that you chose, it's going to spit out a value that lies on a number line. So everybody will draw a number line. And our number line starts at 0, 1 is a critical value, and then it continues up positively, 2, 3, 4, 5, 6, all the way up to infinity. In this case, yeah, E will always be positive because the whole function is wrapped inside an absolute value symbol. So the values that come out will always be positive. The smallest this thing could ever be is 0, and then it just gets bigger as you go. So what is this thing called E, elasticity? It's describing customer mindset. All right, so if that's the first thing you want to think about, is describing customer, you can either call it mindset, or you can call it customer behavior, or customer predictability, or how customers feel about your product. So let's go through here and look. The very first option says if E is less than 1, so that means we're right over here. We would say that that demand is inelastic. So I'm going to go right here, and I'm going to call this whole area here inelastic. And then, if E is greater than 1, we say demand is elastic. Now notice, the range for inelasticity is between 0 and 1, whereas the range for elasticity is between 1 and infinity. So it looks like the elastic range is much bigger. But in theory, there's just as many numbers between 0 and 1 and between 1 and infinity. That's a little bit abstract. But it's true. In calculus, well, forget it. The point is, even though they look very different, they're both used just as much. Okay, so, and then when E equals 1 exactly, we call that unitary. And unitary is actually the goal. You want to choose a price and a quantity that leads you to equals 1. So we could go ahead and say that that's our goal. Our goal is to choose a price and a quantity that when you plug it into the elasticity formula, it equals 1 exactly.
So everything from one to maybe last.
Yep, everything, if your E equals, 1.05 or a 2 or 3, then your demand is elastic. And if you're over here, E equals 0.5, then your demand is inelastic. Okay, well that's just the definitions and the vocabulary. What does this really mean? Let's look at E as less than 1. In this case, raising prices will increase revenue. So let's write out that whole thing. Raising price. Raise price, raise revenue. What does that mean? I want you to imagine. Let's just think about pizza. You run a pizza shop, and you're currently selling your pizzas for $15 per large. Okay, 15 bucks. And you say, man, I really want to make more money. So instead of charging $15 for my pizza, I'm going to charge $20 for my pizza. Now, customers could go one of two ways with that, right? If you're currently selling your pizza for 15 and then you all of a sudden hike your prices to 20, which customers are going to keep buying your pizza?
The loyal.
The what?
The loyal ones.
Yeah, very loyal, right? It means they really like your pizza, and I don't care that you raise the price. I still want your pizza, right? So that's one thing that could happen. What's the other thing that could happen if you raise from 15 to 20? Yeah, what? Yeah, they're gonna go somewhere else, right? They're like, forget you. I don't need your pizza. All right, your pizza's average. I'm going somewhere else. Okay, well, what this says is that when E equals a number between 0 and 1, it's telling you that actually, if you raise the price, you'll raise the revenue, meaning people will keep buying your pizza. Okay, so you go ahead and raise that price. Go for it, because they're going to keep buying it. So what this describes right here of inelastic demand is that customers are going to continue to buy and want your product. So what you can say here is customers will keep buying. So now what's a product that's inelastic? What is a product in your own life that if they raise the price on you, you're just gonna keep on buying it? Yeah, milk is a good one. Like certain standard food crops that you really like to buy and eat. Maybe milk, maybe soda, you like soda. Maybe your favorite food. Avocados, you're like whatever, avocados are expensive, I keep buying them because I love my avocados. What's something else that you'll all keep buying no matter what? Shoes. Shoes? Well, maybe, you might buy a substitute shoe though. You might be like, oh, these shoes are too expensive, I'm just gonna go get some.
Cool. So like just in general, if your shoes get torn up.
Well, that's true. You will eventually need to buy new shoes, but you might go buy the less expensive kind.
Yeah, that's the thing.
Okay. Well, yeah. So this one depends, right? Because we're trying to talk about customers who, no matter what, they're going to keep buying. And I can see how you might go ahead and keep buying those shoes. But somebody else might not. So what's a universal product that we're all going to keep buying no matter what? I think what?
Food.
Yeah, food. Probably.
Yes.
Gas. Yeah, very good. I was about to say gas. Like, you've all experienced the cost of gas go up and down and up and down over the last, 10 years? Gas has been kind of crazy. What was the most expensive gas was? $6? I never saw that. I thought I saw $4.50, maybe almost $5. Yeah, about 5. Now, when the gas was at its most expensive, like $4.50, $5, were any of you like, maybe I'll try this? No, I don't think so. Maybe you thought it in your head, but I don't think any of us actually changed our driving behaviors. We were just like, bummer. Gas is more expensive. I'm going to keep buying it.
I wouldn't go food. I wouldn't. That's enough. I wasn't going to places where I was.
Okay, well, maybe you cut back on your behavior a little bit. Yeah, maybe you didn't. That's a good idea. We all should. But the key thing is that even if the price of gas goes up, we're still going to keep buying it. And so gas is something that's definitely inelastic because we tend to need it no matter what. Anyway, and so some food, we might buy less expensive food, or we might choose to shop somewhere else. But certain things we're going to keep buying anyway. Another thing I think is somewhat inelastic is like the iPhone. People who like iPhones like their iPhones. And I've seen the price of iPhones go from $350 in the beginning to now iPhones are almost $1,000. And people just keep buying those iPhones. So I'm going to write iPhone here. But no matter what here, I like somebody used the word loyalty. And I thought that was really good. Right? So inelasticity means loyalty. And by the way, what does elastic even mean with rubber band? Yeah, elastic means stretchy. Inelastic means not stretchy. Inelastic means rigid. Rigid. I'm going to keep doing what I do. I don't care what the price is. I'm going to buy it. right? Okay, so that's inelastic. And so if you're a business and you have an inelastic product, it's kind of awesome because you can just keep making it more expensive. And those suckers, I mean customers, are going to keep buying your product, right? Okay, so there's inelastic. So what about elastic? Elastic, raising prices decreases revenue. So raise price, decrease revenue. So going back to the pizza company, you're like, hey, I'm going to raise my prices. You do, and suddenly a whole lot less people buy your pizza. Right? You raised your price, and all of a sudden your revenue went down. Now, why is that? How do they feel about your pizza? Yeah, they're like, whatever. I'm not going to buy your pizza. I'm going to go to Little Caesars. I'll get a whole large for $5. So here, customers will stop buying. And you can see that now in the word elastic demand. The demand, the willingness of the customer to buy your product is stretching. You know, like if the price is good, they'll buy it. If the price is bad, they won't buy it. So that's elastic demand. So what are things that are elastic? What kind of, what? Yeah, maybe a car. Like if the price is too high, they're like, I'm not going to buy a car right now. Yeah, maybe. Things that are completely optional. Yeah, maybe clothes. Yeah, I mean, it really depends on, you know, if you need clothes, if you just want clothes. But really, we're looking at things that are optional. Or maybe things that you'd only buy if you had a coupon. I know that I'm like that. There's certain things that if I don't have a coupon, I'm not going to buy it. But if I have a coupon, I'm like, okay. You know, or some restaurants. Certain restaurants, they have deals. Like this one place I like called Humble Pie, they have a date night on Thursday night. And so my wife and I will only ever go to Humble Pie on Thursdays. Any other day of the week, forget it, we're not going to do it. So that's elastic demand. So how do you all feel about this difference between E equals a number less than 1 and E equals a number greater than 1? So what's your goal as a company then? Yeah, you'd kind of like to be over here because if you raise the price, they'll keep buying it. But now notice, every time you raise the price, your value of E just went up a little bit. Because if you keep raising the price, eventually someone will be like, okay, no, I can't afford this. And then they'll stop, right? So what you want to do as a business owner is hopefully you compute your value of E and you fall over here somewhere. And you raise the price, you raise the price, you raise the price, you raise the price until your E equals 1. And then you're done. And you have found a real good sweet spot. That's the best price. Because if you raise your price more, people would stop buying your product. But you wouldn't want to stay here because right now you can keep raising your prices and people will keep buying it. Doesn't that sound terrible that that's how we're talking about customers? Yeah. But honestly, why not charge more if they're willing to charge more? Right? This is your livelihood. This is your business. You know, why only charge $50 for a service if you can charge $60 for a service? Does that sound mean?
No.
Yeah, business is business. All right, well, there we go. So we have a firm understanding of our concept. So let's go ahead and try it out. We're going to look at number 3. Yes, we did. We're not going to do those at all. So in number 3, it says, here's our demand function. So first of all, it would probably be helpful to just look at the demand function because we haven't studied the square root function before. So let's look at that. That's square root of 325 minus 2p. Oh, X. There we go. Now, as we've noticed before in the past, demand functions have to be downward sloping. And so let's think about what this thing says. The input is price. The input is price. So if I charge $20, how many will I be able to sell? So input is price. The x coordinate is price. I'm charging $20. How many will I be able to sell? 16-ish. If I charge $40, how many will I be able to sell? 15-ish. If I charge $60, how many can I sell? 14-ish. I mean, so far, you know, if I charge $80, I'll still sell 12 of these things. So what do you think? Between I can charge $20 and sell 16 of them, or I can charge $80 and only sell 12 of them. What do you think? Just make a decision right there. Should you charge 20 and sell 16, or charge 80 and sell 12? Let's write that down and make that decision. Should you charge, what was it? 20 and sell 18, which is $360 in revenue, or should you charge $80 and sell 12, And what does that make? Is that $960? I mean, I'll give up to 6 customers. This is me, you know, I want to eat this week. So I would totally give up 6 customers because I'm making way more revenue. But maybe that's not always your choice. Maybe you're like, no, I love my customers. And I'll not make $600 this week because I want to keep 6 customers. And essentially, think about it, $600 for 6 customers. You just paid $100 to each of those customers, didn't you? The 6 customers that you actually had come in to buy your product, you basically just gave them $100 off, or you gave them $100 worth of profits, right? Okay, so that's our demand function right here. So in this case, do we all agree that you should charge more money? It seems like it, you know, because by, well, anyway, that's just off the cuff. So there's our demand function. Now let's actually go do the problem. So what does it say? It says, given the demand function, find the elasticity of demand. Everyone write down the formula first. E equals P over Q, and then the derivative of our demand function. So the first thing we have to go do is actually go find dp. So here's, sorry, d prime of p. So our function was dp equals 325 minus 2p to the power of 1/2. So now we'll find the derivative, which we do the power rule. It's actually a chain rule. We have an inside function as well as the power rule. So I bring the 1/2 down, keep the inside alone, subtract 1 from up there. So minusing 1 is really minusing 2/2, so that's negative 1/2. Times the derivative of the inside. The derivative of the inside is just negative 2. So far our d prime of p is equal to, let's see, I can multiply the 1/2 times the 2. So half of 2 is 1, and that's a negative. So it's really negative 325 minus 2p to the negative 1/2. Now what does that simplify to? Remember, subtitle of the course is Advanced Techniques for Algebraic Manipulation and Simplifications. We have to do all this work to finish simplifying. The negative exponent means push it down into the bottom, and the 1/2 means square root. So we end up with that. There's our derivative. Okay. Well, so there's our d prime of p. Now what's p and what's q? What's p? Price. And so they told us up front that they want to charge $6. So that would be our p. So p is 6. But what's q? Yeah, q in this case is quantity. And in this case, quantity is what d of p tells us. So actually, you know, it'd be even better in this formula. Instead of q, we should just write d of p. Because then we're not sitting there trying to translate everything back and forth. It's really just p over d of p times d prime of p. And that's our actual formula, right? So now we actually have to plug 6 into that. So watch what I'm going to do now. Since that's our formula, I'm going to go ahead and write down 6 over d of 6 times d prime of 6. Does everyone agree? So, folks, we could go about doing this in one of 2 ways. We could, and actually here, I'm going to go down here, do that one in a second. What I like to do is find general formulas. So what I'm going to do first is just plug in everything the way it is. So this would be p over the square root of 325 minus 2p times negative 1 over the square root of 325 minus 2p. Sorry, I kind of changed tracks there. On the one hand, yeah, sure, you can just plug 6 into each of those and then compute each one separately and then plug all the numbers in. But I want you to see what the formula looks like. What happens? We plug in p, we plug in the original formula d of p, and then we write down the d prime of p formula we got. And what do we end up with? In the numerator, we just have negative p. And in the denominator, we have root something times root something. What happens when you multiply a root times itself? The root cancels out. That's really root something squared. So we just have 325 minus 2p in there. It is important that we finish this part up here. Again, you can always just plug 6 into each of those and get a number. But now we have a nice formula there, and now we know that we're going to plug in 6 for P, and we're going to actually compute our value for elasticity. So now we have negative 6 over 325 minus 2 times 6, which is negative 6 over 325 minus 12, 13. Now, without doing anything on your calculator, 6 divided by 13, is that a number smaller than 1 or bigger than 1?
No.
Yeah, smaller. That's a very small decimal, like 0.03 or something like that. And so our elasticity is inelastic. This particular product is inelastic. Now let's go ahead and get that decimal just so we can see it. So 6 divided by 313 is absolute value of that. That's 0.019. I want you to look at where we are. 0.019. We're at 2 cents out of $1. Right? We're like way over here. What does that tell you you could do with your price? You could jack up your price a lot. You could charge a lot more. And in fact, we already know that because looking at our example, we know that we should charge at least $20, probably more like $80, maybe even more. I didn't even finish this analysis. I was just suggesting that raising it to 80 is a good idea. And sure enough, if you're only charging $6, you're really undercutting yourself. And you have a long way to go of increasing your price and getting those customers to hand over the money. Because they will.
How does that?
How does what happen?
Like, you can charge that much money, but it's at 6.
Well, yeah, I mean, who knows why they originally set it at 6. Maybe that's just to demonstrate a really, really small elasticity. I mean, these problems are just made up, that's all, right? Okay. So folks, if you did the same thing here, again, you could just plug in each part as you go. So you'd have 6 over d of 6. So if I actually compute d of 6, that would be the square root of 325 minus 2 times 6. That would give me a decimal, 17.69. And then times d prime of 6, which is the negative of the same, oh, no, it's negative 1 divided by that. So that's negative 0.0565. So I have all that, and then I have to divide all that. So 6 divided by 17.69 times 0.0565, which is negative. And I got the exact same answer, negative 0.019, which is 0.01. I don't know. So I showed you this way as well, just because I wanted you to know that if you want to just plug in numbers and get decimals, you can. But I think it's a whole lot better to get this up here, get an actual formula. And for one more reason why this is so exciting. So first of all, we found out that E was 0.019. So our price is very inelastic right now. We should definitely raise our price a lot, and we can make more money. We can make more revenue. How much should we raise our price? What ideally do we want our E value to equal? 1. Because 1 is the changeover point. You can keep increasing until you hit E equals 1. If you increase any more, you'll start losing revenue. You don't want that. So how do we figure out what price P we should charge so that E will equal 1?
So,
Exactly. We could set this equal to 1, right? And that would be fairly easy to do right now. I can take my formula, which is negative P over 325 minus 2P, and I can just set that equal to 1, and then I'll be able to work out backwards what price I should charge. That would be the ideal price. Now, the only tricky thing is here is that we have an absolute value symbol. So recall what that means. I'm going to cover that up. What number must be inside that absolute value symbol such that the absolute value of that is equal to 1? What are the two numbers that could be out of my hand? The absolute value of what is equal to 1? 1 or negative 1. Right? Those are the only two numbers that can be out of my hand right now. So that means I have to solve two equations. I either solve negative P over 325 minus 2P is equal to 1, or it could be that negative P over 325 minus 2P is equal to negative 1. Right? Those are the two possibilities. And what we're going to do now is use this elasticity formula to actually solve for the price that I should charge that would give me the most revenue that I could possibly want. So in this particular case, I'm going to multiply my denominator off to the other side. So that's negative P equals 325 minus 2P. And then I can push my 2P over to the other side. And that gives me P equals $325. So you can see I could keep on raising prices quite a bit in terms of maximizing my revenue. Now solving this one over here, negative p equals -1 times 325 minus 2p. Because I'm moving that denominator up to the other side. That's negative p equals negative 325 plus 2p. And so, oh, what do you know? It ended up solving the exact same formula, or it ended up with the exact same result. So what that means is that either way, I should charge $325. Yes, Andy?
Isn't that one you'd subtract?
Did I mess up?
I think it's 325 divided by.
Oh, you're right. Silly me. Thank you, Henry. Okay. Yeah, I would have to subtract 2p. So that's minus 3p. Yeah, okay, then divide by 3, and p equals 325 divided by 3.
It's still positive. That's 25.
It won't necessarily, it's 108.3. Okay, all right, well now this is good to think about. So I just solved for a particular value of p. So now let's think, which one of those can I actually do? Because it is going to give us two answers. Because there's two equations to solve, and one of them will be realistic, and one of them won't be realistic. So let's look at our original demand formula. This is the price we want to charge. So how do we figure out how many quantity we'll sell? Going back to the original D of P. If I now look at that, if I solve D of 325 versus D of 108.3, what are the two answers that I get? Well, first of all, if I plug in 325, what happens? Worse than 0. 2 times 325 is 650. 325 minus 650 is the square root of negative 325. Yeah, so that's not even a thing. I can't charge $325 because nobody would buy the product, right? Look back at my. Here it is. What am I saying then? Price. Oh yeah, I mean look, the graph literally ends at 162. So if I actually charge $325, how many people are going to show up to buy it? Literally none. The graph doesn't even exist there. So, on the other hand, if I plug in 108.333, then I will find out how many people actually buy it. So 325 minus 2 times 108.33333, that's the square root of 108.333, which is 10.4 people. That's my quantity. There. So if I charge $108, now look at my analysis over here. If I charge $108, then I will sell 10.4 of them. Now, obviously, we're going to have to work out something with rounding, right? It's either actually 10 or 11. So you'll have to think about which one you want to actually sell. But now if I multiply that out, 108.33 times 10.4, well, I did that one. 108. There, that's $1,126.66. All right. Well, so what do you think about the power of this elasticity formula? Yeah, it's a pretty good formula because it's just taking another perspective on how much should I actually charge. And the goal, of course, is to get our E to a value of 1. Okay, my phone went off, so let's take a break. Then we'll come back and we'll do a couple more of these. So the time's 12 o'clock. Let's be back at 12 o'clock.
Some problems we skip, you would encourage us to do them, but they're not, like I don't need to have them on there.
Yeah, no, you don't have to do them at all. You can feel free to not do them. Essentially, I put them on there when I was feeling optimistic, like, hey, let's do all these other problems too because I'm super geeky and I love these problems. But they weren't strictly business related, so I wanted to focus this on what we really need to be covering. If I had more time in the day and you guys were all just going to stay here for another hour, we'd go do that.
Oh, we have a new collection. That water bottle is kind of part of it.
Mm-hmm.
So who makes these formulas? That person probably gets paid a lot.
Yeah. Well, it'd be interesting to actually work out that formula.
Analyst, right? Business analyst.
Yeah, somebody who can figure these things out. I'm curious where the formula comes from. Like, Henry, sit down and solve this equal to 1.
Yeah.
See what you get.
Oh, I see. Like
Yeah, what do you even get if you solve that equal to 1?
right? What do we call those? Groups.
Yeah. All right, folks, let's try another one. No, we did a lot of talking up to now, and that is to clarify the concepts, but let's just go ahead and do our computation. The computation doesn't take all that long. And so we'll go ahead and look at item 4. Given that demand function, and just take a peek at it. That's an upside down parabola. It looks something like that. So again, our demand function will always be negative sloping, because as you charge more, people will buy less. So find the elasticity of demand at a price of $7. So let's write down our formula. It's a P over D of P times the derivative, P prime of P. So the first thing we need to do is take our derivative. Our derivative is pretty simple this time. It's just D prime of P equals what? Negative 8P? Right? Yep, negative 8P. So in our formula then, we'll have P over 200 minus 4P squared times negative 8P. And I wrote my negative 8P kind of high up. Actually, I'm going to put it over 1. Because if you're dealing with a fraction, you should go ahead and make it a fraction, and then you can multiply straight across. So we actually have the absolute value of negative 8P squared over 200 minus 4P squared. So that's our elasticity formula. So again, thinking about our number line, if I plug in a value for P, which is really, really tiny, then my elasticity will be really, really tiny. And I just want to keep on increasing my price until my elasticity hits 1. Or if I plug in a value for P and my elasticity value is way over here, I want to decrease my value of P until I get back to 1. So I wonder where we're at in this particular case. Let's plug in 7. So E is negative 8 times 7 squared all over 200 minus 4, 7 squared. What does that equal? This will tell us our current value of elasticity. So Over 200 minus 4. Yeah, did I do that right? I think so. So then 392 divided by 4, 98. Positive 98 or negative 98? It is negative, but then the absolute value sign makes it positive. Okay, so 98. Our elasticity value is pretty big. It's way over here. Not as big as infinity, but it's pretty big. So what does that tell us we should do? We should lower our prices. That is only if we want to raise our revenue. You know, if we have our own reasons for like, no, I want to charge that much because my product is high prestige and that's just how much I want to charge. I don't want to feel like the riffraff can buy my product. I only want, you know, rich people to buy my product. And I don't care if I'm not making as much revenue. But if you want to make more revenue, you would lower your elasticity value down until you get back to 1. So in this particular case, you look at the $7 and you think, gosh, what could we be possibly talking about? The $7 is too much. So what could we be talking about? Like a really good piece of gum. Right, like a really good gum. Not a pack of gum. One piece of gum. That's a little too expensive for one piece of gum. Would any of you, are you curious though, to buy a $7 piece of gum? That could be the next thing. What if that was a thing? You go to the grocery store, it was a $5 stick of gum. Would you do it once? You'd try it once. Yeah, I know you would. All of you would. $5 stick of gum. That could be a new company right there. You're welcome. All right. So at this price, we would say the demand is definitely elastic. Because people who don't want to buy your product won't. And based on this, to increase revenue, we should lower the price. We should definitely lower the price. Because that will have the effect, and this might seem counterintuitive, by lowering the price, you're actually going to boost your revenue. And why does that work? You're lowering your price, you would think you're going to make less money. Yeah, more people show up to buy it. Exactly. See, I'm sure that I could pull off a $1 stick of gum. Everybody would buy that, probably multiple times. Especially if you're going on a date, you're like, I'm going to go give me that $1 stick of gum. Right? All right. Okay, well, now, of course, if we wanted to, we could now solve for the correct price for this thing. So we would take our formula here and set it equal to 1 or negative 1. And that will actually tell us what price we should solve. This is a bonus question. So if I take negative 8p squared over 200 minus 4p squared, that's either going to be equal to 1 or set that equal to negative 1. How do you feel about why we're setting it to 1 and negative 1? Does it make sense why we're setting it equal to both? Yeah, because it's absolute value. All we need is for the thing in here to equal 1. So that thing in there could equal 1 or negative 1. You have to consider both possibilities. So I multiply off the denominator. I have negative 8p squared equals 200 minus 4p squared, which I move the 4p squared over. That's negative 4p squared equals 200. Divide off the 4. Ooh, I can see what's about to happen here. P squared is equal to negative 50. And so the square root of negative 50 is? Yeah, 7.1i. So that's not a thing. So that's not it. So I'm going to do this one instead. Negative 8p squared equals negative 200 plus 4p squared. Now I'm going to bring that 4p squared over and get negative 12p squared equals negative 200. This makes more sense. Divide out negative 12. So p squared is equal to 100 over 6. So 200 divided by 12. 16.6 repeating. Square root that. Okay. The price we should actually charge is $4.08. So apparently $7 was too much. But $4.08 is just right. Now see, I think that would go a long way to the advertising of this product. Like again, go to the stick of gum. How much was that stick of gum? $4.08. Like the 8 cents would leave people wondering, like, man, this is a good piece of gum. Right? Well, not just $4 even. No, $4.08. right. Yeah, plus tax. What would a stick of gum have to have for you to be willing to buy it for $4? Like calories? No calories? Vitamins? Flavor, very long lasting? It cleans your teeth?
Yeah.
Yeah, it'd have to have a lot of things. All right, how does everyone feel about this idea of elasticity? Henry?
So for that one, like the equation, that could be whole, right?
Well, this particular one, a whole?
Or the bottom could equal 0.
The bottom. Oh, I see what you're saying. Yeah, good point. What if you chose the price that would make that 0? Let's talk about that. Thank you, Henry. So when is 200 minus 4p squared equal to 0? That's when 200 equals 4p squared, which is when p squared equals 50, which is when p equals the square root of 50, which is 7.1. So yeah, $7.1 would be 0, which would shoot the value of e up to infinity. And so that's where you get that really, really high value. Yeah, so like they were charging $7, but if all of a sudden you chose $7.10, your value would shoot way up there.
That's the absolute value of the 5.
Yeah, the absolute value of undefined. Well, just in this particular case, I just know that if we keep moving that value towards 7.1, it'd be an asymptote. Yeah. It's not really equal to infinity, it's undefined.
Oh,
But as you get close to 7.1, it goes to infinity. At 7.1, it's undefined. Okay, shall we try one more? So we've seen an example now of both where, now I said skip on this one. So, and in fact, we already did a problem just like number 6. So we might go back to do 5. Okay, no, here, this is just a regular linear problem. Let's look at that. A regular linear demand function. This computation should be pretty easy. So there's our demand function. Calculate the elasticity at $38. Now again, so you notice, looking at $38, we have no idea if that's high or low. If we're talking about gum, too high. If we're talking about an iPhone, too low. So we just have no idea until we actually look at the demand function. So, and then notice they're actually saying, at what price do you have unit elasticity? So in this problem, they are actually asking us to solve for P by setting it equal to 1. So let's go ahead and write down our formula. P equals P over D of P times the derivative. And so our derivative is pretty simple. It's P prime of P equals what? -2. So we plug all of that in. We have P over -2P plus 153 times -2. Henry, will there always be a value at which the function is for elasticity is undefined? Because we always have a demand function which has a variable in it. And where do we stick that demand function? Right into the denominator. And so yes, you should always be able to choose a particular value for P that would make that value equal 0. And so E, the value of E, could shoot up to infinity, or at least head that way. Yeah, so that'll always be the case. Okay, so now what do we have? We have the absolute value of -2p over -2p plus 1. So what is our current value of elasticity? Notice I could use function notation right now and write E of 38. Does that make sense? Like they didn't say that E was a function. You can easily turn E into a function by just using parentheses and say, hey, let's input 38 into our function. So now that's going to be -2 times 38 over -2 times 38 plus 153. Oh, yes?
What would E look like on a graph?
Well, it'd be fun to graph. Here, let's look at it. In fact, graphically, that would be a wonderful idea to look at it. Because then, of course, you're just looking for when E equals 1, right? So E equals absolute value of negative 2p divided by negative, is it -2p plus 53? Did I type that in right? Okay, oh, but not p. Desmos doesn't know p, it only knows x. All right, so there it is. And of course, we want to know when is it equal to 1? So we would want 1, and that would give it to us right here. So graphically, we already just solved it. So now you'll notice that as you start increasing the price, eventually you get to a price of whatever that vertical asymptote is, about 70 something. In fact, it'd be 76.5. X equals 76.5. There's our vertical asymptote. And then if you keep increasing the price, it starts coming down again. Now, does it ever come down again to hit 1? No, because now it's approaching it asymptotically. Now, see, that's interesting, Josh. I hadn't quite thought about that. Like, sure, E will equal 1 over here, but could E ever equal 1 again over here? And if it did, that'd be a little weird. If E could equal 1 for two drastically different prices. So in theory, no, that shouldn't happen. That the other asymptote should only ever approach 1 and never meet it over here. It should only ever reach 1 over here, which is your ideal price. Josh, does that answer your question?
Yeah.
Yeah. And to Henry's point, will there always be a vertical asymptote somewhere? Yeah, because D of P is in the denominator. So provided D of P is a demand function that has a variable in it, then yeah, there will be at least one asymptote. All right, so did we finish this one? We just have to finish evaluating that. So well, of course, I already saw the answer on the screen, but let's 2 times 38 and divide by 38. Oh. Did we get negative 0.98? Negative 0.98, which is really 0.98. Now, that's a nice elasticity value, 0.98. You know, that means you're like right here. And if you're running a business and changing the price would actually be a hassle. Like just imagine, if you want to change the price, you'd have to contact all of your vendors, have all of your vendors change the sticker price, and that would be a lot of effort to go around to everybody. Maybe the difference in revenue that you get by raising your elasticity from 0.98 to 1 would actually not give you as much revenue as the cost of actually telling all of your people to raise the price. Is that possible? And it could be expensive to ask all your companies to raise the price. Because now all those employees have to go around and change all the sticker prices and raise the prices, and let alone manufacturing the product, making stickers on the product. Like it's a book, and the book says $7.95, and you're like, well, actually, I can make more profit if I raise the price from $7.95 to $10. Because then you have to reprint all the next line of books. You have to wait until you can print the next line of books that has the higher price. Oh, I mean, there's so many considerations, right? In any case, what should we do, since we're right here? We should raise the price, right? Because if you raise that price a little bit, and keep in mind, E of 0.98 doesn't actually tell me how much of a price I can do. You think, oh, E 0.98, that means raise the price by 2 cents? No, E is not the dollar. E is just elasticity. So raising it from 0.98 to 1 could be a matter of raising the price by $10, $20, $50. You have no idea. All we really know is that E is less than 1, and we should raise the price. So that begs the question, how much should we be charging? How do we find out? That's what the next question is. At what price would you have unit elasticity? So I want you to have that question in the back of your mind. 0.98 tells us we should increase the price. Well, increase it from $38 to $50 maybe? What if it was merely raise the price from $38 to $38.10? Like, you're like, oh man, this is minutia. What are we even talking about? Well, let's try it. So set your function, which is this, equal to 1 or negative 1. And then find out which one is actually correct. So I'll set negative 2p equal, okay, negative 2p plus 1 equal to 1, or negative 2p or negative 2p plus 1 equal to negative 1. By the way, have we been keeping track about which one has been right so far? Was it negative 1 both times? I mean, you all could check your work on your page. I erased my work. I don't know that there's a pattern. I think you just have to try both to see which one is realistic. Okay, so then this one, negative 2p, ooh, watch what happens here. Negative 2p equals negative 2p plus 153. The 2p's cancel out and we have 0 equals 153. So will this expression ever equal 1? No, because it led to a contradiction. So that value will never equal 1. But can it equal -1? Yeah, -2p equals 2p minus 153. So then I move the 2p over, that's -4p equals 153. And so p equals, oh, I'm on the edge of my seat. I can't wait to know how much should I raise the price to? Oh, 153 divided by 4. Oh no. $38.25. So again, just imagine, you just received the initiative from your company. We got to raise that price. $38 is not enough. Raise it to $38.25. And your customers will still buy it. Right? That's the theory. That's the theory. Your customers will easily fork over $38.25. But raise that price to $38.26, you just lost a customer. Right? As the theory says, you raise that price too much, you just lost the customer. That's crazy. All right. Well, what do we have here? We can save some time to look at the practice test. Oh, in fact, that's all I have gotten to. So here, let's go ahead and flip all the way to the end of the practice test because that's where we see the elasticity problem. And the elasticity problem that I put on the practice test, I gave 2. There are 2 elasticity problems on the practice test. One is a square root and one is a square. So how about, since we just practiced this, everybody go ahead and turn to the last page on the practice test and go ahead and do those last 2 problems right now. Feel free to work with a partner, or I'll just walk around the room and answer questions. But might as well tackle that part of the practice test right now, since we just finished talking about it. But who knows? Lack of evidence is not evidence of lack of evidence. Exactly. So maybe it helped, or maybe I was never going to get sick in the first place. Jared, do you have an interview with us? Or you came straight from work? I didn't say you looked very fancy. That's fine. You're going to put parentheses on that, right? All right, yeah, very nice. Okay. So as you do that first derivative, folks, remember you're doing the chain rule. So you're going to do the derivative outside, leave the inside alone, and then multiply by the derivative inside. And of course, you can go back and look at this problem, which we just did a second. The derivative of -2p is -2, right? Because there was a negative sign on that too. Yeah, there you go. Because that'll affect. Oh, you had it there. Oh, okay, good. What's the derivative of this? 2 times. Right. Well, then you're going to put them together so that it's being squared, and then it cancels. Yeah. What was that? 1.5? Is it being multiplied in 3 times? Oh, where is it? I don't see it. Oh, okay, all right. Oh, I like how you did that. You just went and stuck the 3 up there, and then put the 1/2, the 2 down there, and then left the negative sign up front. That looks good.
Yeah, good. So you had the 1/2, that was the negative. Where's the derivative of the negative 3p? That's part of the chain rule. Okay. Yeah. Yeah, so the chain rule says you take the derivative of the outside, so that's what you multiply by the 1/2 and subtract the 1. Leave the inside alone, which you did, and then multiply by the derivative of the inside. So the derivative of 275 is nothing, and the derivative of negative 3p is negative 3. And there you go, that's the chain rule.
So I just
Yeah, just the negative 3. Yeah, which you can just stick up in the numerator. Anywhere. Anyways. Which one did you do? For the practice test? Oh, good. Oh, this was the point. Where's the practice? Oh, this is the practice test. Oh, okay, very nice. No, that's a 3. Oh, that's what you're just doing right now. Okay, I see.
Okay, I think a lot of you started with the first one, so I'm going to start writing up the work for the first one so you can compare your work. So, UP was 275 minus 3P all to the 1/2. And then we'll do the chain rule. So 1/2 times 275 minus 3P to the power of negative 1/2. And the chain rule says take the derivative outside of the inside alone and then multiply it times the derivative of the inside, which is just negative 3. And then I'd like you all to notice that you all wrote down your answer slightly differently. Like on the one hand, you could do negative 3 times 1/2, and that could be negative 1.5 times 275 minus 3p to the negative 1/2, and then you could push the negative part down. So you'd have negative 1.5 over the square root of 275 minus 3p, and that's what some of you had. On the other hand, you could have pushed your square root part down to the bottom, and then you would have a negative 3 on top and a 2 on bottom. So the 1/2, the 2 goes on bottom, and the negative 3 stays on top. So both of those are perfectly fine. However you did it, both of those look great. Okay, and then we would find our formula. So E equals P, UP, minus P, which would be P, root 275 times negative 3 over 2 root 275 minus 3. Then at that point, everybody should have something that looks like negative 3p over 2 times 275 minus 3p. Because when you multiply the root times itself, the root cancels out. And then I would end up with something like this. 550. So this very last expression, maybe you have it written differently, but that's what I ended up with. Did anyone end up with this? Maybe some of you? Maybe some of you might have it slightly different. So then we would go ahead and plug in the $27. Did anyone else get negative 81 over 388? Or better yet, let me type that in as a decimal. Did anyone else get 0.2087? Better yet, 2088. So, however you did it, when you're all done, you would hopefully have the same decimal as me. Yeah, that's great. And you could have used that expression too. It's fine that you change it to this one, because 3 divided by 2 is the 1.5. So both ways are used.
Oh, and that one was easier? Okay, great. Yeah, hey, whatever you. Have you got the same? Okay. Did it work in it? You got the same value? Did it work? Okay, great. All right, so in terms of answering the whole question, for that first one, we'd say the price is, we'd say the demand is inelastic. The demand is inelastic, which means the people are going to keep buying my product even if I raise the price. Their demand is inelastic, their demand is constant. Their demand is loyal. And that means I should raise my prices and take more of their money. Kind of sounds terrible. My customers are loyal. I'm going to raise my prices. Elasticity?
Yeah.
I think they do use elasticity to describe something. What is it describing? Elasticity. Or what? Collisions?
Yeah.
Oh, sure. You mean like physics?
Yeah.
Oh, okay, yeah. Yeah, for sure. Like purely elastic collisions. Yeah. Okay. Well, I tell you what, we just have maybe 10, 15 minutes. Do you want to flip through the entire practice test and choose a couple problems that you're interested in, and we'll take a look at them? And then I'll do the same thing. Let me go ahead and look through the practice test, and maybe there's a couple that I want to point out to you. Like, hey, make sure you do this and this. So, flip through the practice test, and basically I'll write down a list of numbers on the board, and we'll go through as many as we can. Keep in mind the solutions to the practice test are already posted online, so you can go online and download those solutions. And keep in mind the practice test is due on Thursday. So you need to complete the practice test and then bring it with you because I will collect it as a grade. Of course, I know all of you want to complete the practice test because by completing the practice test, it kind of gives you insight about the actual test. You'd be shooting yourself in the foot if you did not come to class having already done the practice test. Okay, let's see here.
Tuesday is 2.9 due on Tuesday or?
How about we make everything due next week on Tuesday during spring break? Is that better? So nothing's due this week. You can just focus on finishing the practice test and getting ready for the test. Is that the answer you'd like?
Oh yeah, I was going to since we finished 2.9 today, I was really.
Right, it's not due today. Yeah, no, it's definitely not due today. Good point. It'll be due a week from now. Let's say a week. Okay, so now, what questions?
Test can say a little sketch on it.
Make a little sketch. Okay, what numbers would you like to see? Go ahead and tell me some numbers. Say, hey, low one? Okay, 15. Anyone else? 20? 20, isn't that? Oh, that's the other one? Okay. You want to compare? Okay. Any others you want to see? Fatima? Molly? Sarah? 17. Sarah, 17, great. Juan? Josh? What's up? Colleen? JW? Anyone? 6, great. Okay, so I'm going to start backwards since I have number 20 on the board already. So Henry, maybe you just wanted to check your answer. So d prime of p would be negative 8p. And so the whole formula for elasticity would be p over d of p times d prime of p, which is p over 100 minus 4p squared times negative 8p, which would be negative 8p squared over 100 minus 4p squared. Is that what you got? Yeah, so find the elasticity of demand at a price of 5. So folks, when you actually plug 5 in, 5 squared is 25, 25 times 4 is 100, and 100 minus 100 is 0. And so you get something, negative 200, over 0, which is infinity.
So,
I would do that. It's very elastic.
yeah, right. I mean, we're way over here, so very elastic. So we should probably lower our prices, right? And because Josh had us look at the graph, we know now what we were looking at on the graph is that you have something, vertical asymptote, and so we would be here, right? This is where we're currently at, we're at that asymptote. So we definitely need to lower our price until we get back down to a value of 1, right? So that's what that would mean. Yeah. Okay, let's keep going here. I'm going to work my way backwards, maybe. 17. This is the sunglass hut question that we did a little earlier in class. Who said 17? Jared, what would you like? Oh, were you here when we did this one? Yeah. Okay, yeah, I don't think you were. So let's, I'll do an overview sketch of this one. So we have, what's up there? You've got a profit function. Maybe that's sure. This is a really good question, folks. I mean, this is your like really, I don't want to say typical, but like standard calculus question. So you have your profit function. And it says Q is in thousands, so it wouldn't hurt to write quantity in thousands. And then P of Q is total profit in thousands as well. So this is our profit in thousands. And we want to find the marginal profit. So marginal profit is always just the derivative. So we can write MP, that's marginal profit, or you can just write P prime. And so that's going to be negative 0.04 Q plus 4. So I just took the derivative, and that's the marginal profit function, and now we can use that to find our maximum. We want to maximize profits. I mean, 6 to the derivative, set it equal to 0. So I set that equal to 0, and I get negative 0.04 Q equals negative 4, and that gives me Q equals, I think, 100. Right? Yeah. So what is that actually? That's 100,000. So Q is 100,000 sunglasses. And then what is the actual maximum profit? I'll just take my 100 and plug it back into profit. So I plug in 100 and I get a number. So that's the essential arc of that problem, is that you're taking the derivative and then you set it equal to 0, and whatever number you get, you plug it back into profit, and that'll tell you how much it is. Okay, let's see here. I won't be able to get to all these questions. How about 15? Somebody asked about 15. So 15, hey, excellent. This problem is also asking the same thing. What production level will maximize profit? The thing is, they're asking about profit, and so far all they gave you was a cost and a price. So what do we have to first do if you want to maximize profit? That means we want to solve P prime of X equals 0. What do we have to find first? The actual profit. So profit is going to be revenue minus cost. And revenue is always price times quantity minus cost, which they gave us. And in this case, the price, they're just telling us the price is always 1950. So no matter what the price, no matter what quantity you sell, charge 1950. So that means we're going to have 1950 times our quantity X minus our cost function, which is 6450 plus 650X, 4.3X squared. And once we, subtract that, distribute that, rearrange all the terms, negative 0.3X squared plus 1300X minus 6450. Now we have our profit function. You notice a problem like this, the purpose of it is to make you do a whole lot of work before you can even do the problem. It sounds mean, but it's true. You have to do a little work to even come up with a profit formula. Now you can actually take the derivative of it to get that, and then set it equal to 0. And then once you finish solving for X, then you plug it back into the original profit formula, and that will tell you what your maximum profit is. Who asked about 50? I was going to ask, did I answer your question? Maybe I'm the one who said 15. I answered my question. Okay, number 9 then. Now keep in mind, folks, we're just really quickly glancing at some problems from the practice test. you can email me anytime you like. Just shoot me an email, and I'd be happy to go through any of these questions with you via email, or you can come into my office hours tomorrow between 10:30 and 12:30. So number 9, I wanted to point out number 9. This function has a local min and a local max. So first of all, notice it's a cubic. So that means you can expect the graph to look like that. So I have a local max and a local min. What would be a good thing to do first before you even do this problem? Starts with good and ends with graph it on your graphing calculator. Graph it on your graphing calculator, right? Like go ahead and just look at it and see what the answer is. That'd be a real great idea. Just boom, go write down the answers from your calculator. And then go about actually taking the derivative, setting it equal to 0, doing the quadratic formula, right? That's the wonderful part about advanced math classes is you're allowed to use your calculator. So then you take the derivative, set it equal to 0, do the quadratic formula, which would be what? This, and then you factor x minus 7, x minus 1. And so x equals 1 or 7. So hopefully my graphing calculator bore that out and actually told me that my coordinates were 1 and 7. And then I'd plug those values 1 and 7 back into the original function and find out how tall it is and how short it is. And again, hopefully my graphing calculator matches. And keep in mind, when you take a test in here, I'm always happy to show you how to use your graphing calculator. So you can just come up to me during the test and I'll remind you how to use your graphing calculator. We have 1 more minute.
So the one you plug it back into the original function.
Yeah, you plug 1 and 7 back into the original function to tell you how high and how low that one is. I think Rosa asked about number 6. So, oh yeah, good. So when you do problems with position, velocity, and acceleration, in terms of derivatives, it goes the function. Oh. All right. I hate writing on the backboard. The original function is position, and the derivative is velocity, and the second derivative is acceleration. So that's the key thing to keep in mind, is that it goes position, velocity, acceleration. And so number 6, they start out by giving you the position particle, and then you just take the derivative and the derivative again. Does that answer your question? I think you asked about that one, didn't you? Okay. Well, in any case, folks, if you have any questions, I'll stick around. Keep flipping through that practice test. Feel free to come on up to my office hours right now. Yeah.
I'm not sure what I'm doing.
You can take another one. But you have to do it again, though.
Okay.
All right. Anyway, did you find out why the formula is what it is?
I mean, kind of. I didn't really get. I wrote it out.
It's a P over D of P. And D prime.
D of P is the price, D prime of P is the demand at that price.
But we're trying to ask the question, how long can you keep increasing the price to increase the revenue? So like, if this is revenue in terms of price, that's what we actually need. Because that would be easy enough if we just knew revenue in terms of price. But the thing is, we know revenue in terms of quantity. So revenue in terms of quantity gives you revenue. How on earth are we supposed to rewrite revenue in terms of quantity?
Well, revenue is price times quantity.
Oh, revenue in terms of quantity, which is D of P. So that's what we have. We have revenue in terms of quantity, and then we want to find that flat spot, right? Right? So what I really want to do is just find this formula and take the derivative and set it equal to 0, because that would be the flat spot of when I should keep increasing to increase revenue and when I should stop. Yeah, because this is really what we're talking about, is how much can I raise price and still raise revenue?
Well, with that, you're saying it's D of Q.
Oh, yeah. Wait. Well, because, I want price on it, which is D of Q. Yeah, but they didn't give us D of Q. They gave us D of P. Yeah, we usually do.
What's the difference?
Well, as we said, it's just the difference of input and output. But, right, because that's normal revenue. So then what then? We need to somehow find that? Revenue in terms of the price? But they gave us that. So I don't understand. Okay, let's just say that we have this. Let's just say that we have this. And I want to take the derivative. So this is a chain rule. Do the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. And then set that equal to 0. Oh, 0. Okay. Well, then what? That's going to tell us the flat spot. I don't know. I don't know how to get back to that. Plus, there's a thing that if you have the derivative of the inverse function, I think that's equal to 1 over the derivative of the original. There's some formula there. So we should at least be able to find that in terms of L. I don't know. I'll have to spend a little more time on it. I'm curious though. I think we're on the right track, because that's what we want to do, is figure out how much should you increase price and still increase revenue. But to do that, we would need some sort of inverse function.
I know what I'm doing for the next hour.